Yes, friends, let us start with new phase of discussion today, the performance of feedback control systems. Though this is not a new discussion altogether, in some form or the other, what do we need from a control system? How do we specify the performance of a control system? All these has been discussed, in many cases qualitatively. So, I think before we go to the design problem, it will be necessary to specify the performance quantitatively. The discussion today is primarily concerned with the quantitative specification of performance of a control system. Recall the qualitative discussion, for example, to start with. The qualitative discussion, if you recall, the performance called for the stability of the system. The system has to be stable. So, an unstable system is not going to perform. So, the primary requirement on the performance of a system is that the system must be a stable system. The second aspect we discussed qualitatively was on transient response. We want that the transient response of the system should be acceptable. By acceptability, I mean that the system should rise to the desired value quickly and should not have large overshoots, should not oscillate around its equilibrium state before it settles down to the equilibrium state. The third point raised was steady state accuracy. The steady state accuracy is concerned with the steady state response after the transients are over, whether at the steady state the response of the system, the output of the system is equal to the commanded value or not. If not, then there is an error at steady state, and most of the systems will require a very good static accuracy, so that after the transients are over, the output follows the command accurately. The next we had taken was the sensitivity and robustness issues. Sensitivity and robustness issues called for the effect of variations in the system parameters due to errors in modeling or due to changes of the parameters with usage in time. You see that we wanted that the system must be robust, that is, the system must perform acceptably even under the situation that the parameters of the model are different than those used in your control system design. The other point we discussed was disturbance rejection. In this particular case, again the requirement was this, that when the environment affects the system, when the disturbances, uncontrolled disturbances affect the system, then the output should reject their effects. That is, the output should not be affected by this, at least at steady state. During transient state, the effect of the disturbance on the system should die down quickly. So, this is what we qualitatively found is the requirement on a control system. Now, various quantitative relationships for these measures were also discussed, but now coming to the design, what we are going to do is we are going to specify the performance in terms of transient and steady state accuracy. Once the performance is specified in terms of transient and steady state accuracy and a control system is designed in that particular, after that we will analyze that system to see whether other requirements on robustness and disturbance rejection are satisfied or not. I think at this juncture this point must be very clear. I told you this point earlier also, that as far as the current research in control system design is concerned, methods are being developed wherein the sensitivity and robustness can be specified quantitatively right in the beginning, and the design is carried out to meet that requirement on robustness. But since this subject is yet to mature, you see the research in this area started somewhere in early 80s. Since this subject is yet to mature, this subject still has not been brought to the classroom. So, we discussed the classical way, which definitely is going to provide the background for the discussion on robustness also later. The classical way of discussing control system design is to specify transient and steady state accuracy and then analyze the control system design whether it meets your requirements on disturbance rejection and robustness or not. If not, then you re-enter the cycle. After all, design is an iterative process. You re-enter the cycle till you find that your robustness and disturbance rejections requirements are satisfied to a reasonable extent. So, as far as quantitative specification is concerned, it will be on transient response and steady state accuracy. Of course, the stability of the system is the prime requirement, because without stability, without that condition being satisfied, all these specifications do not carry any meaning. So, what we normally do in design, first we find out the domains of various parameters which result in stability, as we have done using Routh stability criterion. Couple of problems we have solved for simple cases of 1 or 2 parameters. So, we find the domains of parameters which result in system stability. Once the system stability is guaranteed, that is, within those domains a suitable search is carried out, so that the transient and steady state accuracy requirements are satisfied. Once those requirements are satisfied, you go back to the original system, simulate the system to find out whether your robustness and disturbance rejection requirements are satisfied or not. Okay. So, with this background, I take you now to the specifications on the transient and steady state performance. Let me take the transient performance. You see that if I have a system, a typical system I could take this way. To simplify the situation, though the discussion can easily be carried out to a more general case, I take a unity feedback system. There is no loss in generality in this, you see. The discussion can easily be extended to a non-unity feedback system. So, now you know that in this particular case, Ys over Rs equal to Gs over 1 plus Gs is the transfer function of the system. You are interested in the transient response of Yt in response to the input signal Rt. Now, look at a practical situation, please. In a control system, you can never decide beforehand as to what type of input signal will be coming to the system. After all, the control system has been designed to take up any situation it comes across, and therefore, the input signal to the control system really cannot be decided beforehand. So, we should use some standard signals, some test signals, so that if this system is designed for those test signals, it should perform satisfactorily for any input signal which it takes up. And you know that the transient performance of a system is dictated by the poles of the system and is really not affected by the nature of the input. You see that the poles, if all the poles are in the left half plane, it has been discussed, it has been proved by now that the system transients will die down, will die out if all the poles are in the left half plane. So, it means as far as the transient performance is concerned, it is based on the system characteristics and not on the input characteristics. And therefore, if I excite the system by any input, in that particular case, all the modes of the system will be excited and we will be able to look at the transient performance of the system. And hence, it is really not necessary to take up more than one inputs, and you know this has already been given to you that the test inputs which we have already discussed are the step, the ramp and the parabola. There is no limit to these, you see, the step, ramp and the parabola. You could extend higher order polynomials as well, but we find that these step in test inputs or standard inputs are good enough to study the performance of a control system. After all, these are not the actual inputs, these are the inputs. If a system is satisfactory with respect to these inputs, it is hoped that it will perform satisfactorily with respect to any input it comes across, and we have to satisfy ourselves that this statement is true. Let me talk of the transient performance first. Now, you see what is the difference if I take a step input, ramp input, parabola input or any other input, when I know that the transient modes are dictated by the system poles, and therefore, one of these inputs will suffice, and obviously the simplest one will be better, and a step input is taken for the purpose. So, it means From now onwards almost exclusively throughout our course, we will be taking step input response of a system to quantitatively specify the transient characteristics of the system. The reason should be very clear, because I am interested to see the behavior of various modes of the system. The input nature is not going to affect the transient modes of the system. So, step input will suffice for me, and therefore, I consider that R t, the input, is equal to mu t, which is a step signal, and let me say that this is the input 1 I could take. After all, if I take a step of larger magnitude, it is not going to change the nature of the response, it is again going to change the only magnitude of the response, and therefore, unit step input is the standard signal we use to study the transient phenomena. Okay? For the transient characteristics, unit step input is the standard input we take. Come to the steady state response now. Now, if I consider the steady state response, now recall what is a steady state response. Steady state response depends upon the system characteristics as well as the input. You consider any situation, take the transfer function, determine the steady state and transient response components of the system, you will find that the steady state component of the system depends upon the characteristics of the system as well as the input function. So, it means I cannot take a single input to specify the steady state performance of a system. Effectively speaking, I should really have the actual input which the system is going to take up, so as to clearly and rightly specify the steady state performance. But since in a control situation, the input is not known to me. For example, take the tracking radar. Tracking radar is going to track the aircraft motion. Now, how do I know beforehand as to what will be the profile of the aircraft motion? It is not known to me. Take a numerical control of machine tool. I cannot say beforehand as to my machine which type of jobs it will do. Will it taper? Will it do a circling job, or will it cut a parabolic profile or any other profile? After all, if I have designed a control system for a machine tool, for a machine cutting machine, it should be able to cut any profile it is called upon to work with. So, naturally I cannot decide the input function for my control system. It could be anything, because it depends upon the user's specification of the job. Consider residential heating system. Well, you see, the effect of the environmental temperature on my control system is going to change from the summer season to the winter season, because the environmental temperature is going to change drastically. So, the disturbance signal also is going to change, and hence I cannot specify the disturbance signal. So, you see that the inputs cannot be specified, and the steady state performance is definitely a function of the input. So, how do we come out of this dilemma? So, you see that a way of coming out of this dilemma is to consider the actual input as a suitable summation of polynomials. In general, let me take a polynomial function R t is equal to 1 over k factorial t k mu t. It is a polynomial function of time. You see that this is sure, I hope you will agree, that you give me any function, well, it will be possible to decompose that function into a suitable set of polynomials. Okay? So, it means if my system is going to behave satisfactorily for all these polynomials, so it means I can really rest assured that the system will behave satisfactorily for the actual input. So, a set of polynomials I am going to take as the standard inputs as far as specification of the steady state performance is concerned. Now, let me take up k is equal to 0. If you take up k is equal to 0, you find that your R t is nothing but the unit step function. It is a 0 order polynomial. For k is equal to 1, R t is equal to t mu t. It is a ramp function. It is a first order polynomial. Now, this point may please be noted that R t is equal to t mu t is a more difficult signal for the system as far as the steady state performance is concerned. Take k is equal to 2, R t equal to 1 by 2 t square mu t. It is a parabolic function. It is a second order polynomial. You see that as you keep on increasing the values of k, the polynomial is becoming, or the input is becoming faster and faster. Okay? So, normally what is seen is that the actual input applied to the system is not so fast as to require k more than 3. Please see, it is only an experimental evidence. It is only the evidence seen in the seen as per the actual usage of the control systems. Mathematically, you require a large value of k to specify any input function as a set of polynomial functions, but actually you do not require more than k is equal to 2, because the system inputs are not that fast. Because these inputs, the second order polynomial or a parabolic function is fast enough, and if a system is able to perform well for the second order polynomial, it is going to perform satisfactorily for any input it is hoped. Now, as you will see when we come to practical systems, you see, normally we do not take even k is equal to 2 for the sake of completeness. Okay, some difficult control problems do require k is equal to 2. But normally k is equal to 2 also is not taken up, k is equal to 1 is found good enough. You will find that k is equal to 2 raises or gives rise to difficult control design problems. Control design becomes most difficult with increasing values of k. So, it means there will be some value of k, maybe k is equal to, I think if I can quote, maybe after k is equal to 4, it cannot be stabilized at all. So, it means the stabilization problems keep on increasing as the k keeps on increasing. So, it means even for k is equal to 2, after all your requirement is this, that all this steady state performance or transient performance has to be satisfied within the umbrella of stability requirements. So, as the order k increases, the stability becomes difficult to maintain, and therefore, larger values of k, though mathematically quite satisfying, but practically will become very difficult. So, k is equal to 2 is almost ruled out unless there is a very specific situation, and as I am telling you, mostly k is, we will satisfy ourselves with k is equal to 1, because it satisfies the practical requirements, it satisfies the industrial control requirements in many applications. Okay. So, I hope this point is now clear, that as far as the steady state performance is concerned, I will be referring to the unit step, the unit ramp, and the unit parabola. Unit parabola, the word unit is coming because its derivative is unity. Okay. It gives you the unit value. So, in this particular case, unit slope value it gives you once you take the derivative of this. R t is equal to 1 over t squared mu t, take the derivative, it is a unit slope. So, let me call this as a unit parabolic function on account of that. So, these are the three types of inputs I will be referring to when I come to the steady state performance specification, but please note that the difficulty of design increases with increasing value of k. Your design is going to be more difficult because you will not be able to maintain stability of the system. Okay. So, with this now I think I can straight away go to the transient performance specifications. Okay. How do we specify the transient performance? I am not taking any mathematical model. I simply say that you go to industry, take any typical industrial control system working there, excite that system by a unit step input or a step input. You see, unit step is only the scaling of the response, it does not, should not make any difference. You just excite the system, the industrial system by a step input, let me call this as a unit step input, and measure the response. The response in all likelihood in more than 70% cases, or even you can take a larger figure, you see, will turn out to be of this nature. This is what I am saying is the industrial scene today. So, it means I am going to specify the performance as such because all these systems are working in industry and they give this type of performance. Naturally, this performance is adequate The reasons will become very clear. Why this performance is better, why the industrial control systems will perform this way if I excite the system by a step input. Okay. Now, you can see that it is a damped oscillation. So, you will note that damped oscillation is accepted. You are not taking a system with no oscillations, because it is not going to be an acceptable system to you, as you will see. So, it means some of the overshoot in the performance is acceptable to you, because most of the control systems are working this way. So, the specification of transient response effectively will mean specifying this curve for a particular system. But if I specify this quantitatively like a graph, in that particular case, you see the control design will become difficult. Therefore, this particular graph I translate into a set of indices. What are those indices, or what are those measures I take? Please see this. First measure I take is this time, the time taken for the response to come to 100% of the desired value for the first time. It will come later also at this value, but this time, which I am referring to as TR, the rise time of the system, is the time for the response to rise from 0% to 100% of the final value for the first time. Okay? This is one index I take. The other index I take is the following. I take this particular magnitude, that is how much it has what is the overshoot, and it is the peak overshoot, as you will see, because the next undershoot and second overshoot, etc., these magnitudes are going to be lower and lower in a damped oscillation. Since these magnitudes are going to be lower, so it means if the peak is acceptable to you, the other undershoots and overshoots also will become acceptable to you. So, MP, the peak overshoot, is the second index which I am going to use. And of course, the time taken to reach this peak overshoot, TP, I will call it peak time, is another index. I will write the words here. The rise time, TR, I need not write the definition. I hope this is clear now. The peak time, TP, the peak overshoot, MP, and what else? The next and the last I take is the settling time. The settling time, you see that if I give you an exponential function e to the power of, let us say, exponential function I give you e to the power of minus t by tau. This system, this particular function settles to the 0 value only as t tends to infinity. So, mathematically speaking, the settling time of this function is infinity, but practically if I consider, this particular function can be said to have settled down when this particular value is negligibly small, and the word negligibly small depends upon the application. You may say that if it has settled down within 2% of the desired value, okay, you can find that the system function is said to have settled down completely. So, what I want to say now, this is a higher order system, not necessarily a first order function. So, if you take the mathematical response, in this particular case, exact settling time will turn out to be infinity. T tends to infinity will be the time required for this particular response to exactly come to steady state. But what we are going to do is to specify a perturbation band, a tolerance band, so that if the system settles within this particular band, practically you will consider as if the system has reached the steady state, though exact value of 100% or exact value of 1 it is yet to go to. But within this tolerance band, if the system has reached, in that particular case you can say that the system has settled completely, and this tolerance band is normally taken as 2% of the final value or 5% of the final value, depends upon the application. If the application requires a larger static accuracy, in that particular case 2% of the tolerance value is taken, otherwise 5% of the tolerance value may turn out to be acceptable. So, as per the graph you find that, yes, please help me, what should be the settling time? Could I take this as the settling time? because once the system has entered this particular band, as per this graph it is not coming out, and if the response having entered this particular band is not coming out, you can say that the system has settled within the accuracy of the specified tolerance band. So, I can say that this is the settling time of this system. Okay. And lastly, this, let me say, settling time, TS, let me call it. Lastly, let me say the steady state accuracy. Steady state accuracy I will take separately, because steady state accuracy, as we have seen, is not specified only to a step input, it is specified to step, ramp and parabolic inputs. So, only if I am considering the step input response, I can consider only the transient response specifications. Now, you can see that if I give you these 4 parameters, you can almost reconstruct this step response, and hence the complete graph of the system is more or less specified if I give you these 4 values TR, TP, MP and TS. Now, what is the requirement? The requirement is this, you see that the TR should be as small as possible, because if TR is not small, if it takes larger time, then your system is a sluggish system. It takes lot of time to rise to the value you require. The TP should also be small, so that whatever is the peak, it should come quickly, and then the system should settle down. TS naturally should be small, MP should also be small. So, I want all these values to be small, but unfortunately these things are conflicting, as you will see. If you tend to make one value small, the other becomes larger, and that is why the design problem. Otherwise the design would have been a set of mathematical equations to solve it, You see, the design does not turn out to be a set of mathematical equations for solution. The design is an iterative process, because these requirements cannot be satisfied simultaneously. These are conflicting requirements, as will become clear shortly. Okay. Let me go to the steady state performance specifications. Steady state performance specifications, ESS is equal to limit t tends to infinity RT minus YT. Recall the original block diagram I had given you. The original block diagram, I may redraw it here because it is a simple one, plus minus R, E and Y. This is a unity feedback system I have taken. Therefore, this E is nothing but the system error, it is R minus Y, and value of this E as t tends to infinity, because the system will completely settle down as t tends to infinity mathematically. So, using this mathematical relation gives you the steady state value, and this RT now could be a step input, a ramp input or a parabolic input. So, it means as far as the specification on steady state performance is concerned, the user may give you the specifications like this: ESS to unit step and or ESS to unit ramp and or ESS to unit parabola. This point may please be noted, this and or, because if the requirements on steady state accuracy are not very stringent, in that particular case a very simple situation is that only steady state error to unit step is specified. You will find that your design problem becomes very easy. As a designer, you will be very comfortable if such a situation is there. The design problem will become more and more complex if more and more specifications are given. For example, if unit ramp steady state error is also added, well, the design problem becomes difficult, and it still becomes more difficult if I specify the steady state error to unit parabola as well. So, these are the specifications, and in any particular control design problem, user tells you that these are my specifications on transient and steady state accuracy, and now you give a design for me. And once you give the design, of course, the user will definitely want that the actual system, when your design is implemented on an actual system, it should operate satisfactorily. Otherwise, what will happen when the user takes your design from your table and implements it in the actual situation, it will not work. The reason being, the model you have used on your table is definitely different than the actual process he is going to work with. So, it means your design has to be robust. So, it means every design has to be declared complete only after extensive simulation study. So, what you will do is, whatever design you have carried out, you will go to the computer and vary the parameters of the model. Varying the parameters of the model means going closer to the actual physical system, because you really do not know how the actual physical system is going to behave. The simulation you can do is, the best possible tool available in your hand is this, that you vary the parameters of the system and implement the design you have made for the nominal parameters. If your design gives satisfactory performance for all the variations, all the reasonable variations in the parameters you have made, in that particular case you are sure that when the user takes your design to the actual application, it will give him satisfactory performance, and that is the final stage of design. Okay. So, with this background, I think now we can enter into the design cycle straight away without wasting time, unless there is a question. If there is a question, I like to answer, otherwise I enter into the design cycle straight away. Fine, I take it positively, no question means you have understood me. Fine. The design cycle, I start with a standard second order system. I do not mean that the actual systems in industry will be second order systems, I do not mean that, but I definitely can guarantee you that if you have understood the design for a second order system, you will be able to extend this design cycle to any system you come across, and that is why the design of a standard second order system is extremely important. So, this is my starting point. Once I give you all the tips for this standard second order system, the extensions will be very obvious, and be it a 10th order system, the tips we are going to finalize for a standard second order system will be applicable there as well. Okay. So, do not think that it is a fictitious situation, though it is a mathematical situation, not a real life situation. So, to capture this mathematical situation, I take GS as S plus 2 zeta omega n. This is the R input Rs, this is the error Es, and here is the output Ys. This I consider as a unity feedback standard second order system. Okay. Now, let me carry out everything I have talked of, the transient response specifications, the steady state response specifications, as far as the standard second order system is concerned. I am looking for, I first analyze this system. Design means what? Design means I am going to introduce a controller here. Let me say that this D is the controller, DS, so that this particular standard second order system meets the specifications you impose on this system. That is the design exercise. But before I take up this DS into the loop, I simply analyze my system first. That is, I determine those measures, those indices for the given system without any design. Let me call it that this is the analysis problem I am going to carry out first, and after the analysis I will incorporate this DS, the controller, into the forward loop, and then see how to get the value of DS, so that the specifications on transient as well as steady state accuracy are met. Okay. So, for me now it is only GS in the forward loop, I do not take DS. So, GS is equal to omega n squared over S into S plus 2 zeta omega n. So, what is the closed loop transfer function please? Ys over Rs equal to, help me please, omega n squared over S squared plus twice zeta omega n S plus omega n squared. This is your standard second order system you are already conversant with. Zeta and omega n, you know their physical meaning. Zeta is the damping ratio, omega n is the undamped natural frequency. You know zeta is equal to 0 is an undamped system, zeta between 0 and 1 is an underdamped system, zeta is equal to 1 is a critically damped system, and zeta greater than 1 is an overdamped system. You know this, and you also know that the characteristic equation of the system is del S equal to S squared plus 2 zeta omega n S plus omega n square. Now, from this point onwards, please see, any equation I give you, any statement I make, I tell you, you will be using that statement till the end of this particular course. These are very important quantitative relations I am going to give you, and therefore, I want you to absorb these relations, okay, permanently in your memory in addition to your notebook, please. The characteristic equation is known to you. Help me please, what are the characteristic roots? These are the characteristic roots, okay, minus zeta omega n plus minus j omega n 1 minus zeta squared under the root are the characteristic roots, please. Give me the sketch of these roots as zeta is varied, please. Help me please. Real S, imaginary S. Well, zeta is equal to 0, please see, is going to give me the roots as plus minus j omega n, j omega n here minus j omega n here. These are the roots, please. J omega n minus j omega n are the two roots corresponding to zeta is equal to 0. Now, how about zeta is equal to 1, please? Zeta is equal to 1 is going to give me the double root, please see, zeta is equal to 1, you substitute, it is going to give me the double root at minus omega n, okay. So, now it means for the critically damped system, the two roots are at this particular point, and for an undamped systems, the two roots are on the j omega axis. And if I draw this semicircle, you will find that this is actually the locus of the roots as zeta is varied between 0 and 1. Take a typical value, come on, take this value please. At this particular point, give me the real part is going to be equal to minus zeta omega n, and the imaginary part is equal to j omega d is equal to j omega n 1 minus zeta squared under the root. This is your j omega d. The omega d, as you know, is the damped frequency. So, minus zeta omega n is the real part of the root. Please see that this zeta omega n in my discussion is going to have very important meaning, and you can see that this zeta omega n magnitude corresponds to the real part of the complex conjugate root pair. Help me please, if I draw a line here and take this angle as theta, could you give me the value of theta please? I want you to give me the value of theta. This value theta is going to be obtained from this particular triangle. Yes, what is cos theta is equal to? Cos theta is going to be equal to this value, this is omega n, this value divided by this value. What is the radius? The radius of the semicircle is omega n, is it okay? The radius of the semicircle, you can see that the radius of the semicircle is, you can see this point also, that this is minus zeta omega n, this is omega n 1 minus zeta squared under the root. Take the magnitude of this is going to be omega n, and therefore, cos theta is going to be equal to zeta. If you need this explanation to this, well, tell me please. Cos theta, this theta I am going to call it as the damping angle, because this theta is not a function of omega n, it is a function of zeta only. I repeat this diagram. You see that this is corresponding to zeta is equal to 0. The locus is a semicircle with radius equal to omega n. The locus is a semicircle with radius equal to omega n. This particular root is minus zeta omega n, and this particular part, and this is j omega d is equal to j omega n 1 minus zeta squared, and this I have taken as theta. So, I hope this is very clear from this particular diagram that this line is a zeta line, as it is called, or damping line, because this angle is a function of damping only. So, the damping angle theta is equal to cos inverse zeta. Okay. So, it means if I give you the value of zeta, the root, the corresponding root is definitely going to lie on this angle. So, how to draw it? Suppose I give you zeta and omega n, say zeta and omega n are the two parameters which describe the personality of a standard second order system. How do I get the roots? The roots graphically I can get this way. Draw a line here at an angle theta is equal to cos inverse zeta. This is your zeta line. Cut a magnitude equal to omega n. These are the roots of the corresponding system. These are the closed loop poles of the system or the roots of the characteristic equation. The real part is obviously minus zeta omega n, and the imaginary part is j omega n 1 minus zeta squared under the root. The damped frequency is coming over here. So, this way we have the relationship. Please see what I want. This point is very important here. As I said, what I have told you, that if I give you the values of zeta and omega n, you can translate these values into closed loop poles. So, is it not equivalent that the zeta and omega n of a standard second order system are specified, or the closed loop poles of the system are specified? This statement, though at this particular point does not look to be very important, is going to be the basis of root locus design. The zeta and omega n are the characteristics of the transient response of the system. If I specify zeta and omega n to you, I can translate this into the desired locations of the closed loop pole, and the design procedure then will be to force the closed loop poles of the system on the desired location. Equivalently will mean satisfying the transient performance specifications. Okay. So, it means the required zeta and omega n have been translated into these locations for closed loop poles. Fine. As I said, primarily we are interested in an underdamped system. So, look at the underdamped system, please. Underdamped second order system, omega n squared over s squared plus 2 zeta omega n s plus omega n squared. This is the response function. You will note that I have taken Rs is equal to 1 by s, a unit step function. So, this is the response function for me, you see, and I want to analyze this particular response function. We have already done in this particular course. You can otherwise independently try it again. The inverse Laplace transform of this is such a standard function that almost all control engineers will remember it, you see. So, I do also remember it. This is sine omega n 1 minus zeta squared t plus theta, where theta equal to cos inverse zeta. This is the function I get, please, yt, the response of an underdamped system between zeta is equal to 0 to 1, that is your closed loop poles are complex conjugate poles. This is the response function. This is, as you see now, is the damped natural frequency, and theta is the damping angle coming over here. Now, if I make a sketch of this function, a typical sketch, something we have already done, this is your unit step function. A typical sketch is like this. Now, the two curves, the envelope curves, we have already discussed, you see, if you look at your notes. These are the two envelope curves, and let me write the functions for these envelope curves. It is 1 minus e to the power of minus zeta omega n t divided by 1 minus zeta square under the root, and this curve is equal to 1 plus e to the power of minus zeta omega n t 1 minus zeta squared under the root. These are the two envelope curves, please. Now, you see that these envelope curves has an important role to play as far as the transient decay of the system is concerned. You can note that the faster these envelopes decay, faster is the decay of the actual response, because the response always stays within these two envelopes, and the time constant of this envelope, help me please, what is the time constant of the envelope, which is an exponential curve? The time constant tau, I want to get answer from you, 1 over zeta omega n. That is why I said that zeta omega n product plays a very important role. zeta omega n, inverse of zeta omega n, gives you the time constant of the envelope of the standard response. Okay? And you know that the lower the value of the time constant, the faster is the response, and that is the faster is the decay of the system. So, the decay of the envelope curves is a guideline to the decay of the actual response of the system. This will come in our discussion later. Come on, couple of equations. I have some 10 minutes available, and with your help I hope I will be able to derive these equations quickly. I write yt equal to 1 minus e to the power of minus zeta omega n t divided by 1 minus zeta squared under the root sin omega n 1 minus zeta squared t plus theta. This is the response, please. You note one point, you see, the t is appearing with omega n in this particular expression. This is omega n t here, this is omega n t here. So, it is more convenient for me to make a plot with respect to normalized time omega n t rather than time t. I can make a plot, you see, for various values of y. I am taking on horizontal axis the normalized time omega n t. So, if I take this normalized time omega n t, zeta is the only parameter left, you see. So, y is the response and this 1 is the input. I can take now the response with respect to zeta. As you will visualize, for lower values of zeta, the response is going to be more oscillatory. So, let us say that this is the typical response for zeta equal to 0.1. Okay? Now, you increase the value of zeta. Increasing the value of zeta, your response may look like this. Say, let us say that this is for zeta equal to 0.5. These are the rough sketches I am making. If you increase it further, you can go to zeta is equal to 1, and zeta is equal to 1, you know that it is a critically damped system. This is zeta is equal to 1 is the response curve where the oscillations just vanish. Okay? For a value of zeta just lower than this, there will be an oscillation. Now, if you increase the value of zeta, it is very well known to you that the system becomes sluggish, though there is no overshoot, but the system response to settle to the value will also be very large, and normally this response for zeta greater than 1 is not acceptable unless there is a very specific application. Normally zeta greater than 1 in a control system situation is not acceptable to us because the response becomes very sluggish. Now, you find in this particular case, you see observations, qualitative observations, lower the value of zeta, lower the value of TR, please. So, it means your rise time is lower for lower values of zeta, but lower the value of zeta, larger is the peak overshoot. You can see that at this juncture, qualitatively, without even going to the quantitative expression, you find that the peak overshoot and the rise time are conflicting each other. Well, a lower peak overshoot and a lower rise time are the requirements of design. Rise time will mean speed of response, and peak overshoot corresponds to relative stability. Say large peak overshoot means there is a tendency to go towards oscillation and the system becoming unstable. After all, this is your nominal system, keep in mind. The actual system parameters will be different than the nominal system, and therefore, there is a possibility that the actual system parameters may drive this system to instability. So, it means a very large peak overshoot is not acceptable to you, and similarly a large rise time is not acceptable to you, and these two are conflicting requirements, as you say. And similar situations you are going to get as far as settling time and the peak time is concerned. Let me go to the quantitative situation, please. Help me, please. From the response yt equal to this expression which we have written zeta omega n t, give me the value of TR, please. Come on, independently do it and then compare with the result I am going to write. I want the value of all the 4 indices for this particular expression, please. The first index is TR. So, it means the equation to get TR is going to be yTR equal to 1 for the first time. okay, that is going to be the value of TR, why TR equal to 1. So, in this particular case please see e to the power of minus zeta omega n TR divided by 1 minus zeta squared sine of omega dt plus theta should be equal to 0. This is what I want for the first time. Okay. This will become 0 only when the sine term becomes 0, and sine term will become 0 only when this is equal to pi. The other values will also give you, but for the first time if you are considering, so I will take it pi. So, in that particular case please say I am getting TR equal to pi minus theta divided by omega d as the expression. TR equal to pi minus cos inverse zeta over omega n 1 minus zeta squared under the root is the expression for the rise time. You have to keep that in mind, because I will be using this quite often in my discussion throughout. You can see that rise time is a function of both zeta and omega n, and I will resolve this conflict of conflicting specifications, conflicting design requirements. This will be resolved later. At this particular point you can just see that TR is a function of both zeta and omega n. Okay. Come on, help me please for TP. TP, the time to peak, how do I get that please? You see the response is of this nature and TP means this time. So, it means actually it is nothing but a point of extrema of the response. It is a point of extrema, and I want to get the value of Tp where the derivative of y is equal to 0. So, set the derivative of y equal to 0 please. So, you see that y again 1 minus e to the power of omega n 1 minus zeta square t plus theta. This is your y please. Yes, give me the derivative please, dy by dt equal to, and then I will manipulate that derivative and give you the expression. This is zeta omega n e to the power of minus zeta omega n t, the derivative of this, divided by 1 minus zeta squared sine of omega dt plus theta. Okay. What next please? Minus, taking the derivative of this now, e to the power of minus zeta omega n t divided by 1 minus zeta squared cos of omega d t plus theta into what? Into omega d. Please see this expression, all of you please satisfy yourselves that this expression is okay. This is the derivative I have taken of the value of y, and naturally this equal to 0 at the extrema. So, the negative of dy by dt expression at this particular, this I am taking equal to 0. Why negative of this? Please help me. So, now in this case you see I have to take this value equal to 0, and from there I get the value of time t, which I call as the Tp time. Help me please evaluate the manipulation of this. What I am doing it this way, omega n e to the power of minus zeta omega n t divided by 1 minus zeta squared under the root out zeta sine omega dt plus theta minus, help me please, what shall I write here? What shall I write here if you are with me? 1 minus zeta under root cos omega dt plus theta. This should be equal to 0. Okay. Now, give me the manipulation of this equation please. I make you recall that diagram I had given you regarding the damping angle. You see that this was your damping angle theta, and here is a typical point which corresponds to complex conjugate roots. This is minus zeta omega n, and here I have omega n 1 minus zeta squared under the root j. Of course, the magnitude is this. Help me, what is zeta equal to? Zeta equal to sine theta, and 1 minus zeta squared under the root is equal to cos theta. Okay? You can see it very clearly from this particular triangle that zeta is equal to So, sorry, zeta is equal to cos theta, 1 minus zeta square under the root is equal to sin theta. Therefore, the expression cos theta sin omega dt plus theta minus sin theta cos omega dt plus theta equal to 0. Okay. Now, simplify this, this is going to be sin A minus B. Sin A minus B, it means sin of omega dt equal to 0. Theta goes away, sin of omega dt is equal to 0, and this will occur, you see that. Now, see the expression sin omega dt equal to 0 will occur at many points, but you are interested in the peak overshoot. The peak will occur at the point corresponding to pi. It cannot occur at 0 because that cannot be the peak, it can occur at pi. So, Tp is going to be equal to pi over omega d equal to pi over omega n 1 minus zeta squared under the root. Another important expression I want you to remember. Now, if I want you to find the time to first undershoot, please, you take here 2 pi. The time taken to first undershoot will become 2 pi by omega d. The time taken to second overshoot will become 3 pi by omega d, and so on. However, in my design cycle, I will really not be interested in that. I will be interested in peak overshoot, and the peak overshoot is given by this expression Tp is equal to pi over omega d. Once you have taken this value, since it is just, yes please, just a minute, just a minute please, just this expression I wanted to complete. What is MP? Okay, I think you can go quickly once you derive MP for me. What is MP? MP is going to be equal to the overshoot over and above 1. So, can I write this is y Tp minus 1? Okay. So, y Tp minus 1, okay, since the time is already over. So, I give this result to you, it's simple manipulation. In the expression for y, you substitute Tp and manipulate MP, you are going to get this as e to the power of minus pi zeta over 1 minus zeta squared under the root. It is a simple manipulation. In the y expression which we have derived, substitute Tp is equal to pi by omega d and simplify, your peak overshoot turns out to be e to the power of minus pi zeta over 1 minus zeta squared under the root. Thank you. I will continue with the discussion on the transient performance specifications.